In today's lesson, we're going to do some real organic chemistry. And by that, I mean that we're going to look at how we change one functional group to another. And specifically, we're going to focus on the mechanism of that reaction. Now, we've looked at some mechanisms before with acid-base chemistry, but that was just acid-base chemistry. And the mechanism we're going to look at today is the first functional group transformation. And that's really what an organic chemist is paid to do, is to transform one functional group into another functional group. The specific functional group transformation we're going to look at is the conversion of an alcohol into an alkyl halide. And while alcohols and alkyl halides are just scratching the surface of the type of things that an organic chemist should be able to do in the laboratory, we have to start somewhere. And this particular mechanism has a name, which is not always the case. It's referred to as an SN1 mechanism. We're going to go through and pull out what those letters in SN1 mechanism mean when we get into the details of that mechanism. But first, before we get into the chemical reaction, let's pause a minute to consider the physical characteristics of alcohols and alkyl halides. And here I have a table of data. And you'll notice that I have propane, ethyl fluoride, and ethanol. And the reason that I've chosen these three compounds is because of their structural similarities. Propane, ethyl fluoride, and ethanol differ at this third position. This is a methyl group, which has an atomic mass of 15 grams per mole. This is a fluorine with an atomic mass of 19 grams per mole. And this is they call this a hydroxy group or an alcohol with an atomic mass 16 from the oxygen, 1 from the hydrogen, 17 grams per mole. And the reason that I said those numbers was to show you that their masses are pretty similar. We're going to see in a minute that when you start changing the molar mass, you see some very large differences in the boiling point, which is kind of the main physical property we want to focus on. So the first thing I want to do is establish that I'm dealing with compounds that have fairly similar atomic masses, and that allows us to then think about their boiling point not as a difference of mass, but as a difference in the intermolecular forces of attraction. Earlier in the semester, I tried to get you to focus on three primary forces of attraction, these intermolecular forces of attraction, IMFs. And the first one that we looked at was dispersion force, well, not the first, but we've looked at dispersion force interactions, dipole-dipole attractions, and the special class of dipole-dipole attractions called hydrogen bonds. And if you learned that section well, you should kind of already have looked at these molecules and started to categorize them based on those forces of attraction that they have. When molecules are small like this, and 3 carbons is pretty small, the dispersive force interactions tend to be fairly weak. And a generally nonpolar hydrocarbon really only has dispersive forces of attraction. And the experimental way of assessing forces of attraction, the strength of forces of attraction, is to look at the boiling point. Propane here has the lowest boiling point. This is negative 42 degrees on a Celsius scale. That is lower than negative 32 and much lower than 78. So this has the lowest boiling point. And what that says is that at the lowest temperature, I can still get these molecules to break apart. And that tells us that they're fairly easy to break apart compared to the other two. When I move to the ethyl fluoride or fluoroethane, depending if you want to use substitutive or functional class nomenclature, this is functional class because it has a space. So the ethyl fluoride right here has a significant dipole. And you can actually measure experimentally the dipole using an apparatus that is difficult to explain in a video, so don't worry about it. But the dipole of ethyl fluoride is the highest of these 3 compounds. The question asks, why is fluoroethane, or ethyl fluoride, depending if you want to use substitutive or functional class nomenclature, why is it the most polar? And that's based on these data over here, where the net dipole of a hydrocarbon is 0. When you attach a fluorine to it, then it's 1.9 units of polarity, which is D, or ethanol, which is 1.7. And it all comes down to electronegativity. The fluorine is the most electronegative element. It pulls electron density over on top of itself better than the oxygen does because oxygen is the second most electronegative element on the periodic table under normal conditions. Electronegativity is a little flexible, and we don't like to tell you that because then we can't hold you accountable when you don't memorize the electronegativity values. But it works often enough to say that fluorine is the most electronegative and oxygen is second most, and then chlorine, and after that it's just based on proximity to fluorine on the periodic table. General chemistry. In organic chemistry, we look at this fluorine and think, wow, that's really that's really electronegative, so that pulls the electron density over, so that generates the largest net dipole. Oxygen's not quite as strong, so second largest dipole. So if fluorine has the largest dipole, why then is it not the highest boiling point? Ethanol, with its highest boiling point of 78 degrees Celsius, means that you have to put a lot more energy into a solution of pure ethanol in order to coax the ethanol molecules into separating from each other. It's much easier to coax the ethyl fluoride molecules into separation. And in fact, the fluorine really doesn't do much for the boiling point compared to not having a fluorine on there at all. And this has to do with hydrogen bonds. So when you consider how two molecules of ethanol, these are two molecules of ethanol, they could interact via a hydrogen bond. And a hydrogen bond has three players. The hydrogen goes in the middle. It's the center of the Oreo cookie. And on the outer edges of your hydrogen bond, you have to have either an oxygen, a nitrogen, or a fluorine, and it can be any one of those three on either side. So you could have an oxygen here and a nitrogen here, and it's still a hydrogen bond. The fact that they're both oxygens just makes it a type of hydrogen bond. When you look at what ethyl fluoride could do in a solution just containing ethyl fluoride, then it doesn't make a hydrogen bond because your Oreo has a hydrogen in the middle, and that's good, but one of the outer cookies is a fluoride and the other one is not. It's not an oxygen, a nitrogen, or fluorine. So this is not a hydrogen bond. It's just a regular dipole-dipole attraction. A run-of-the-mill dipole-dipole, not that impressive. Let's now expand our data table to look at a lot more compounds. So you'll see over here a variety of different alkyl halides mixed in with some alcohols. And in no particular order over here, none at all. And so what I have here are boiling point values, and you'll notice that the highest boiling point values correspond to hexanol. Well, that's an alcohol, and that makes sense. It has the hydrogen bond interactions. But the second highest boiling point is bromohexane. That's just a regular alkyl halide, and it does not have any oxygens, nitrogens, or fluorines, so it can't make hydrogen bonds at all. So just comparing these two, hexanol with bromohexane, what they do have in common is the same number of carbons. They both are a hexane, and this one has an OH group attached to it, and this one has a bromine attached to it. If we look at a similar comparison of 6 carbons with 1 bromine versus 6 carbons with 1 alcohol, so that's a pair. They have the same number of carbons with a bromine or an alcohol, and their boiling points are very similar. Now let's look at methanol versus bromomethane. And the reason that this pair is comparable to that pair is that this is 1 carbon with a bromine and 1 carbon with an alcohol. So what I've done here in this pair is I have the same number of carbons, and I'm just changing out a bromine or an alcohol. Over here, I have the same number of carbons, 6, and all I'm doing is replacing a bromine with an alcohol. These two have very similar boiling points, and these two do not. Very dissimilar boiling points. And what this tells us is that hydrogen bonds, which definitely exist in alcohols and definitely do not exist in alkyl halides, are very important for small molecules. But as those molecules start to get larger and larger, the hydrogen bonds become much less important. To appreciate that, let's just take a look at hexane. And if you have 2 straight chain hexanes that kind of sit next to each other, they stack well. That leads to an increase in your boiling point because with that nice stacking surface, they form strong dispersion force interactions. If we now just tack an alcohol on the end here versus a bromine, the alcohol makes hydrogen bonds. And so you would think, well, then hexanol would have a higher boiling point than hexane. And it does. Because hexanol gets all of this dispersion force interaction and it also gets a little bonus here from the hydrogen bonds. But one hydrogen bond has trouble competing with the strength of 6 carbons worth of dispersive force interactions. And what we notice if we take that alcohol off and replace it with a bromine, and then we ask, well, when you have 2 of these, how well do they stack together? And the answer is they stack nicely, spatially, but this bromine is the massive cloud of electron density. It's this huge bowl of jelly. And dispersion forces are created when atomic electron clouds start to oscillate in harmony. And if you have a bromine on there with this massive electron cloud, because it has 35 protons and therefore 35 electrons, that's a lot more electrons than you see with a carbon that only has 12 electrons. Bromine has a lot of electrons, and it doesn't hold them very tightly, so they really start to sway, and that produces a large dispersive force interaction. That idea of an atom having a large electron cloud that kind of rumbles back and forth like a bowl full of jelly is given a more technical description as polarizable, or also commonly said, but not as technical, soft. They call this a soft atom because its electron cloud can oscillate, move back and forth. That's what oscillate means. And if you put 2 soft atoms next to each other, they make very nice dispersive force interactions. Oxygen, on the other hand, is what's called a hard atom because it's not polarizable. The electron cloud on oxygen, so oxygen is element number 8 on the periodic table. It has 8 protons and 8 electrons. It has a small electron cloud, and because it's so electronegative, it holds that electron cloud very tightly. And even more, it also holds the electron cloud of the neighboring atoms very tightly. So it kind of locks everything down. So not only does it participate in extremely weak dispersive force interactions because its electron cloud doesn't oscillate, it also forces the neighboring atoms to weaken their dispersive force interactions as well. And so when you have 2 hexanols like this, they form good hydrogen bonds right here, but the dispersive force interactions, especially on these carbons that are near the alcohol, is quite weak. It finally gets stronger as you move away. So what the hexanol gains in the hydrogen bond, it kind of loses when you get out here to the end and you start looking at the impact on the dispersive force interactions. And that's the principle behind the functionality of Teflon. So Teflon contains a whole bunch of different, it's a hydrocarbon with a bunch of fluorines attached to it. And I'm not exactly sure what the exact chemical ingredient that is the active ingredient in Teflon is, or if it's simply kind of a potpourri, a mixture of different fluorocarbons, just not chlorines, just fluorocarbons. And so Teflon contains these fluorocarbons right here. And what happens with the fluorocarbons is the fluorines lock down the electron clouds of all the carbons. And so this just doesn't participate in good dispersive force interactions. And the fluorines also struggle to make hydrogen bonds because they don't actually have hydrogens connected to them. So this makes a surface that just doesn't have a lot of good stickiness to it. That's why Teflon coating on a pan produces a non-stick surface. The fluorines lock down the dispersive force interactions, and when you cook eggs on a Teflon pan and you slowly drive off all the water, and you're left with just kind of a clump of egg protein, when it sits, proteins, they're a little more complicated than a hydrocarbon, but you can imagine that the protein tries to stick next to your Teflon coating on your pan, but because the fluorines don't prevent good dispersive force interactions, then the eggs can kind of slide off of this thing and don't make good dispersive force interactions. There's a pretty good movie about the environmental consequences of fluorocarbons that stars Mark Ruffalo that came out not too long ago. And if I don't ever update these videos, at some point, not too long ago, will be decades. But for now, it's a relevant show and worth your time as a chemist, especially as a student of organic chemistry, because you'll notice there's certain conversations that make a lot more sense if you have a basic feel for what alkanes are and what fluorine does when you attach it to an alkane. The movie's called Dark Waters. I had to look that up. Okay. So this question right here, explain bromohexane, explain why, there should be a Y in there. Explain why bromohexane has nearly the same boiling point as hexanol, but bromomethane's boiling point is much lower than methanol. And so bromomethane and methanol are small molecules. For small molecules, hydrogen bonds have a very large effect. as molecules get larger, and by that I mean that the size of the electron cloud goes up, then the dispersive force interactions start to become more important. And then there's also kind of that special consideration that alcohols actually start to lose their appeal, because as the molecules become larger and larger, then they become more reliant on the dispersive force interactions. But oxygens that you find in alcohols, they weaken the dispersive force interactions because they're too electronegative, and they prevent the neighboring electron clouds from oscillating. This means they're not polarizable and they're hard atoms. So let's go back up and look at the previous question of, well, why does methyl bromide have a higher boiling point than methyl chloride? So again, I'm switching back and forth between functional class and substitutive class nomenclature to give you some experience with them. Functional class nomenclature has this space, substitutive class nomenclature does not. So up here I have them in substitutive class nomenclature, chloromethane and bromomethane, and you'll see that their boiling points are different, and the chloromethane has a smaller boiling point, a lower boiling point. It's more negative, and that's because the bromomethane has a larger electron cloud. The dominant intermolecular force of attraction in alkyl halides is the dispersion force interaction. And this interaction is increased, it's strengthened when you have larger electron clouds. Bromine is a much larger atom than chlorine, and it's also less electronegative, so it's softer, squishier, more polarizable. More polarizable atoms lead to stronger dispersive force interactions. All right, now we're ready to do the first part of this, and that's complete the table. And so this question of sink, swim, or mix refers to what happens when you mix these compounds over here specifically with water. And so I should mention that in water. Sink, swim, or mix in water. And there are two different kinds of compounds here. We have alcohols and we have alkyl halides. They have different rules. So first, let's focus on the alcohols. Methanol is called wood alcohol. I don't know why that is. I think they originally distilled it off of fermented wood. But when you mix methanol with water, it mixes. And so they form a single layer. And you might have seen this now that you're not taking a laboratory. Hopefully you've noticed Italian salad dressing at some point in your life, and that illustrates the idea that water and oil don't mix. Well, mix is a crude, imprecise term. We prefer the term miscible. So when two liquids mix together, then they are miscible. So methanol and water are miscible in any amount. You can have 90 grams of methanol and 100 grams of water, 100 grams of water, 90 grams of methanol. It doesn't matter how you mix the two together. The hydrogen bond interactions between the alcohol and the methanol it was welcomed in by the hydrogen bond network of water, and they mix together. The difference between methanol and pentanol is that with pentanol, you have this increasingly large hydrocarbon chain. And we already looked at the structure of hexanol, so let's kind of think about what hexanol looks like from the perspective of water. So with hexanol right here, you have, from the water's perspective, oh great, I can make hydrogen bonds with this portion of the hexanol, fantastic, come on in. And so when you put hexanol into water, then you get energy out of the bonding that occurs between the hydrogen bonds of water and the hydrogen bondability of the alcohol. The problem with hexanol, though, is that this hydrocarbon tail represents just a tremendous amount of baggage. Think about kind of a crazy ex-girlfriend or ex-boyfriend who, well, there was a part of them that was very appealing, but then as you got to know them, there was just all the craziness. So from the water's perspective, this portion of the molecule is unattractive. Water can't do much with the hydrocarbon, and so it comes at a cost. This portion of the molecule disrupts the hydrogen bonds that water previously had enjoyed, and at some point that's no longer enough to offset. So this problem right here is too much, and the alcohol portion of this and its hydrogen bond appeal is just not enough, and the water stops dissolving more hexanol. And so we measure this in terms of solubility. If you take 1 liter of water and start pipetting in hexanol very carefully, you can get about 5.9 grams of hexanol into the water. And I didn't specify the temperature, but we assume room temperature of about 25 degrees Celsius. If you increase the temperature, you can get more of a solute to dissolve into the water, but 5.9 tells us the story that's important. There is a limit to how much hexanol water will take. For pentanol, there is also a limit, but it's a higher limit. And the reason for that is pentanol gets rid of part of the craziness, gets rid of this methyl group right here. And now from the water's perspective, every time it gains because of the hydrogen bond with the alcohol, it does have to deal with this 5-carbon tail. That's kind of a pain. But it's willing to do it to a greater extent than a 6-carbon chain. And so as you start to clip off carbons, then you're going to see the solubility go up. Butanol would be more soluble than pentanol. This would be propanol, would be more soluble than butanol. Ethanol is infinitely miscible with water. I think vodka is our best attempt as humans to try to produce a pure ethanol mixture. The proof of vodka is twice the percentage of the solution that is alcohol. So if you have a 90 proof alcoholic beverage, that means it's 45% ethanol and 55% water. Once you get to 200 proof, which would be 100% ethanol, then it feels like unfair labeling to refer to it as an alcoholic beverage. At that point, it's just reagent-grade ethanol. We actually have reagent-grade ethanol in the laboratories, and they spike it with usually a little bit of something that tastes awful, very bitter flavor, so that people are not encouraged to steal the reagent-grade ethanol and take it home for home consumption. In order to get rid of that impurity, you can actually boil off the ethanol and distill it, that's what it's called, or you can actually freeze it. Different alcohols have different freezing points, and so there's special laws in the state of Utah to discourage people from increasing the concentration of ethanol by either distillation or freezing unless they have a special permit. So what's the point? Well, the smaller the alcohol, the more likely it is to be miscible. This is still considered miscible, and the cutoff for miscibility is about 6 carbons. So a hexanol is the largest hydrocarbon chain that you would generally expect to observe in an alcohol that is still miscible in water. As you go to heptanol and octanol and nonanol, then the solubility starts to drop off so quickly that we just end up with a solution that is immiscible. That leads us to this question. You have 2 unknown alcohols, and they're not totally unknown. One of them is butanol, 1-butanol, and one of them is 1-heptanol. And you have to figure out which one is which, and so you measure the solubility in water. One of the unknown alcohols has a solubility of 90 grams per liter, and the other unknown alcohol has a solubility of 1.1 grams per liter. And so based on the trend that we saw up here for pentanol and hexanol, you expect a larger number of carbons produces a less soluble alcohol. So this 1.1 grams per liter must go with the larger hydrocarbon chain, the 7 carbons in heptanol. The position of the alcohol will also affect this number right here. And it does it in not a very predictable way. So if you start incorporating branches in this, you can start to affect that solubility. That's why there's not like a clear cutoff between soluble and insoluble, or miscible and immiscible for alcohols. But once you get to about 7 carbons, then the solubility gets so low that we're just going to refer to that as immiscible. We're going to say that you really can't get enough heptanol. 1.1 grams in a full liter of water is not a very impressive amount. But 90 grams in a full liter, now that's impressive. So 1-butanol is definitely miscible. 1-heptanol, if I were to put it in this table right here, let's see if we can add a row. We cannot that way. Insert rows above. Well, I messed that up. So we're going to put 1-heptanol in here just to kind of get a feel for it. And you ask, well, why isn't there a 1 with pentanol or hexanol? Well, that's because it's assumed. So I'll go ahead and get rid of the 1 and just assume that. I don't know what the boiling point is, but we can kind of estimate what that is. But in terms of sink, swim, or mix, it's not going to mix. And so it's going to either sink or swim. And so that's the next question we need to get into. What happens when you have an alcohol inside of there that is immiscible, that does not react? And the answer is, well, it's based on the density. the density of water is 1 gram per mil at most temperatures under most conditions. And under other conditions, it's still pretty close to 1 gram per mil. Notice that all of the other alcohols, methanol right here, and pentanol, and hexanol, all have densities that are in the ballpark of 0.8 grams per milliliter. And that actually is kind of the default assumption. If somebody tells you I have an alcohol, they don't tell you what kind of alcohol it is, guess the density for $1 million, you would say 0.8 grams per mil. And if they were honest, they would give you the $1 million. If they were dishonest, they would complain about you didn't give them enough significant figures or some nonsense like that. So heptanol right here is going to be immiscible. We assume that its density is going to be the same as the other alcohols that we saw. The fact that the density goes up with pentanol, hexanol might be a trend, but I don't have enough data to say for sure. But it's immiscible and it's going to swim. Okay? And swim is that's kind of an untechnical way of saying that, but it would be the top layer. And what would happen is, now heptanol is a clear liquid and water is also a clear liquid. You would pour the two into the same container, let's say in equal volumes, 50 milliliters of each. You shake it up a little bit, and then you would hold that container up to the light and look at it, and you would see a line where the two liquids were separated. And if you kind of jiggled the flask a little bit, that line would wave. It's quite pretty when you mix those together if you take the time in the lab to appreciate just kind of the beauty of two immiscible liquids of the same color and the line that they produce where they just don't mix together. I think it's pretty. Okay, the boiling point right here, well, if we look at trends, methanol is 65, pentanol is 138, hexanol is 157. So I would estimate that this would be in the ballpark of 100 and, let's say, 70. Okay? It's going to go up by progressively less and less with each additional carbon. So the fact that this was a gap of 19, this would probably be a gap of less than 19, but probably more than 10. I don't know without looking up the data. So you don't have to incorporate this into your table, but it might be helpful for you to understand what it is that this table is really trying to teach you. And that's this concept that alcohols generally mix with water until they get to about 7 carbons and larger. Then they become immiscible. Because alcohols will have a density lower than that of water, they would be immiscible and they would be on the top layer, and their boiling point will go up with the number of carbons, but they get a really nice boost right at the beginning because of the strength of the hydrogen bond interaction and how dominant that is with small alcohols. So now let's change topics and look at the alkyl halides. And I went ahead and filled in the first part of these, and all alkyl halides are immiscible in water. And you can actually put alkyl halides in water. If you took chloromethane, which is methyl chloride is a functional class name, that's pretty toxic. And you were to mix it up with water and allow the two liquid layers to separate, because they will, and then you were to just pour off the water layer, I would not drink that. Because even though water and chloromethane are immiscible, there is still going to be some small amount of chloromethane that does successfully mix in the water. But not enough. It doesn't kind of cross a threshold of 1 gram per liter to be really kind of in the miscible range. So we consider all alkyl halides to be immiscible in water. And whether they're on top or bottom depends on the density. So chloromethane has a density of 0.92. That is a smaller value than the density of water, so we would expect it to float. It would swim. The top layer is where we'd find it. Bromomethane has a density much greater than water, and so you would expect to find that on the bottom. It would sink. Chlorohexane would be on the top layer, and bromohexane would be on the bottom. And I'm just going here based off the densities. Dichloromethane right here has a density greater than 1, and so that would be on the bottom. It would sink. What trend did you observe? Well, hopefully you noticed that bromines always sink. Hey, you have a bromine here that's going to sink. This bromine is going to sink. And that's true for iodines as well. Chlorines will sometimes float, the first two, the chloromethane and the chlorohexane, but then sometimes they sink, the dichloromethane. And in fact, it's easier just to remember the alkyl halides that float. And they are, if you have 1 chlorine on there, then they're going to float. Once you get 2 chlorines or anything heavier than chlorine, then it's going to sink. So most alkyl halides are going to sink. The exceptions are the monochloroalkanes, one chlorine. What about fluorines? Well, two responses. One is fluorines just really don't show up much in organic chemistry because either they're too reactive and they blow stuff up, or they're not reactive enough and nothing happens. They just kind of are an extreme molecule. But the second answer is it's complicated. When you start putting fluorines on things, they actually have such a low boiling point for the same reasons I talked about with Teflon. They just don't form good dispersive force interactions. That is really hard to collect density data because the density is a question of liquid state. And if the boiling point's really low, then they're never in the liquid state. And so you really can't figure out what their density is. So that's a complication. But ignoring all those complications, we generally expect fluorines to be less dense than water. That's kind of a general rule. And I looked at a table of data one time, and it's not even that consistent. So if you see a fluorine, hopefully it's just got one on there. And I think I have one on the homework here. Did I get rid of it? Yeah, I got rid of it. Yeah, I got rid of the fluorine example. I used to have one, but I got rid of it. And so don't worry about fluorines. Just ignore those. We don't worry about those because organic chemists really don't care much for fluorine. Okay, last question. And this question is actually kind of the big picture, the focus of this particular lesson. And so now that you've hopefully gotten a feel for the physical properties of alkyl halides and alcohols, now let's look at what happens when we convert an alcohol into an alkyl halide. And that's exactly what happens when you mix tert-butanol with hydrochloric acid. Now, hydrochloric acid is what you call something when you put it in water. So hydrochloric acid is HCl in water. If you don't put it in water, then it's still a gas, and we don't call it an acid because the hydrogen's still attached, and it's called hydrogen chloride. I have to say that in the name or it's going to bug me, but you can just call it hydrochloric acid, and that's approximately true enough that it won't mess you up at any point in your discussion with people about organic chemistry. So we're going to mix these two together. We're going to mix tert-butyl alcohol right here, or tert-butanol is a substitutive class name, with hydrogen chloride or hydrochloric acid. The first step of this reaction is an acid-base reaction. And if you don't feel like you could predict this without memorizing it, you kind of have to memorize a handful of these mechanisms. And then after that, you can start applying your memorized mechanisms to other cases. So you kind of have to memorize this. The tert-butanol right here is an acid. Sorry, it's a base. It's a base. And the base reaches out with its lone pair. A Lewis base is an electron pair donor, picks up the hydrogen off of hydrochloric acid, and we end up with a protonated tert-butyl alcohol. This is called an alkyl. An alkyl oxonium ion. That's what we refer to these as. Generically, it's a tert-butyl oxonium ion is more specific, and this is a protonated alcohol. And hopefully you remember your pKa values. Both of these are acids that you should be familiar with. When an oxygen carries a positive charge, its pKa is in the ballpark of -2. So the pKa here is going to be about -2. It's about a -2. And this hydrochloric acid right here is a strong acid. And so equilibrium will favor the formation of the weaker acid. So this arrow right here is not an equilibrium arrow because the reverse reaction is so infrequent. This largely protonates this effectively, and you end up with most of your reagents over on this side. And notice that I didn't bother to redraw the chloride ion. When we're showing an organic mechanism, the only thing we really care about are the carbons. And since the chloride kind of came and deposited its hydrogen on the carbon-containing chunk, and then it disappeared, unless it's specifically involved in the next step, it's not going to show up, and it's not involved in the next step. It is a general tendency of alcohols to fall off. Oxygen's a very electronegative atom right here. You've penalized it with a positive charge. It's irritated like a petulant child. It just takes its electrons and goes home. Takes its ball and leaves the court. And so this right here represents the formation of a specific class of compounds called carbocations. Carbocations are where you have a carbon with a positive charge. Cation means positive charge. So this is a carbon, that's a cation, a carbocation. And this carbocation is a tertiary carbocation. Tertiary because the carbon is connected to 3 other carbons. And carbocations are very difficult to make. In fact, this is another case where the equilibrium of this reaction, I'm going to show equilibrium arrows, it wouldn't be fair to show it kind of like this as an equilibrium process. Instead, what we're going to do is show an unequal equilibrium. And so the reverse arrow is very significant, and the forward arrow is teeny. Meaning that even though this reaction will occur some of the time, as soon as it happens, that water that took off is actually more likely to just kind of jump back on again. So the equilibrium right here does not favor the formation of the product. And it kind of stalls and goes back to this. And we'll deal with why that's kind of a big deal in just a second. But we need to kind of now think about big picture, what are we trying to do? Well, big picture, we are trying to convert an alcohol into an alkyl halide. And so now we bring that chlorine back in again. And it's totally fine for the chlorine to disappear and kind of float away and then come back when we need it. Because the chlorine does not contain carbons, it has second-class citizen status, and it goes away until you need it again, and then you just call it back. All right. And what this chloride will do is it will plug its electron density into that carbocation. And this overwhelmingly favors the formation of products. So the equilibrium on this one definitely leads us to produce tert-butyl chloride. So this is a chlorine, and we're going to get rid of that hydrogen right there and put the lone pair on there. So these are the steps that occur when you convert a tertiary alcohol, because the alcohol is connected to a carbon bound to 3 other carbons. A tertiary alcohol, when it reacts with a halogenic acid, whether it's hydrochloric acid or hydrobromic acid, will undergo these exact 3 steps, where this is step 1. And you don't have to label these, but I'm going to refer to these steps repeatedly, so I want to give you a label of what I'm talking about. This is step 1, and this is step 2, and this over here is step 3. These 3 steps are going to be very similar, even if I change that from a chlorine to a different halogen, and even if I go over here and change around the hydrocarbon portion of this, we still expect for these 3 steps, or something very similar to those 3 steps, to occur. Okay, I cleaned up my steps a little bit just to kind of put them up and out of the way. You'll notice that in the previous mechanism, I drew it from left to right until I ran out of space, and then I went straight down. Sometimes we're going to run into mechanisms that involve 10 steps, and you start snaking your way across the page as you're writing those out. And so you just follow the progression of the arrows, and that helps you see which step is next. This particular mechanism is referred to as an SN1 mechanism. I went and talked to a dentist a while ago, and he asked me, what do you do? And then you mumble incoherently. I teach organic chemistry while my mouth is full of his hands, and somehow he knew exactly what I said, which is an amazing skill. And he goes, oh, organic chemistry. I remember organic chemistry, SN1, SN2, E1, and E2. And that was it. That's all I remembered out of organic chemistry. So I guess in order to be a dentist, you are 1/4 of the way there if you can understand this SN1. I was disappointed that those are all the things that he remembered from organic chemistry, and have not been back since to that dentist. Okay, so this SN1 reaction, now what do these mean? Well, the S tells us that we did a substitution. We substituted this alcohol for that chlorine. The 1 tells us that the rate determining step involved 1 molecule. Now, I'm going to come back to that in a second. In general chemistry, the 1 would mean that the overall kinetics of the reaction are first order. And organic chemists have a different way of looking at that, but that statement's true, that 1 means that the kinetics are first order. The problem with saying the kinetics are first order is, in order to know it's first order, you kind of have to run an experiment. And if you remember interpreting that data in your general chemistry courses, it involves some math, you did some algebra, Sometimes even the quadratic formula showed up in that. So it's kind of a pain. Those kinetic experiments are not how we're going to predict whether or not it's SN1 or SN2. SN1 is first order, SN2 is second order. E1 is a different type of reaction that is first order, and E2 refers to that other type of reaction called an elimination. That's why it starts with the letter E. That's second order. So the 1 tells me the order of the reaction. The N tells me that there is a nucleophile that's involved in a critical step. And it's kind of, I don't feel like we should have that N in there because it's not very easy to tell which step is critical, but we're going to look at the last step right here. In this last step, this chlorine is donating a pair of electrons. That's the definition of a nucleophile, something that donates a pair of electrons or a Lewis base. So this is a substitution that involves a nucleophile, and they refer to this as an attack because a nucleophile kind of throws its electrons in there aggressively. A substitution that involves a nucleophilic attack where the overall kinetics are first order. So how would I know that the kinetics are first order without running a kinetics experiment? And that's what I've got going on down here. This is an energy diagram. So on my y-axis, I have energy, and on my x-axis, I'm going to have reaction progress. This is similar to the concept of time, not identical, but close enough that we can just think about this as time. And we're going to kind of draw, hopefully this sketch works. So I'm going to start off that my reactants start at some inherent energy state. So I'm going to assign an arbitrary energy state to the combination of terbutanol and hydrogen chloride. Every chemical reaction has some type of activation barrier. So they start off at some inherent energy state, and then they're going to go uphill over some activation barrier, and then they're going to come downhill. Now, whether or not they come downhill to an endothermic point, that would be they end up at higher energy, or an exothermic point, is sometimes difficult to predict. I'm going to go ahead and draw the exothermic point because I've done this before. And the activation barrier for this first step is actually quite small, so I'm going to crunch that a little bit. The reason that I know that it's exothermic is because equilibrium favors the formation of my product. And that's based on the fact that this acid is weaker than the hydrochloric acid. So I made the strong acid pKa equals about -2 over here argument earlier. And if equilibrium favors the formation of one side, then that means that side is at a lower energy state. The second thing I did was kind of crunch this down. I should crunch it just a little bit more for perspective's sake. Acid-base chemistry is very fast. And the speed of a reaction has to do with how quickly it hops over this energy barrier. So this first acid-base step is fast, easy, and spontaneous, meaning that we're going to go from some energy state, we're going to protonate this to form a weaker acid, which means we're going to drop in energy. So I'm going to try to redraw that entirely. So it looks something like this. Now the second step, you'll notice I drew the equilibrium arrow, that's a little steep, as not favoring the formation of the product of this step. This arrow here goes way back. And the reason that it goes backwards is because over here, everybody has an octet. Over here, this carbocation no longer has an octet. It only has access to 6 electrons. Carbocations are generally very unstable. And they are a defining feature of SN1 chemistry. So SN1 chemistry typically involves the formation of a carbocation. And you can't say that in reverse. Just because you have a carbocation doesn't mean you went SN1. But if it went SN1, then it's very likely that you have a carbocation. And this carbocation right here is the highest energy step of the entire reaction. And the last step is where an ion crashes into that carbocation. Now, organic chemists do not typically run their chemical reactions in water as a solvent. Instead, we use organic solvents, typically just hydrocarbons. Hydrocarbons do not stabilize separated charges. And so it is a general principle in organic chemistry that if you have a step that goes from having separated charges to a neutral molecule like that, that's going to involve a large downhill drop in energy right here. So the total energy diagram for this reaction shows 3 distinct steps. And the steps are these humps. This is step 1, The second hump is step 2, and the third hump is step 3. And these steps right here exactly correspond to kind of this arrow showing you that during this first process, the alcohol reaches out and picks up a hydrogen. And during the second process, the water takes its electrons, falls, and makes a carbocation. And during this third process right here, the chloride captures the carbocation, and we go down to a very low energy state. Now you might ask yourself, well, how important is all of this for me to know? And the answer is, well, you can learn it now, or you can learn it next time you take organic chemistry. Conceptually, these SN1 reactions show up over and over and over again, not actually because they're that important, it's just that they illustrate some very important concepts to an organic chemist, specifically these concepts. First, every chemical reaction you should be able to break up a chemical reaction, meaning I reacted this alcohol with this hydrochloric acid and I got this product. An organic chemist needs to be able to break up that big picture reaction into the individual mechanistic steps. An SN1 reaction occurs often enough that if you memorize these 3 steps, and they are protonation of the alcohol, second step is formation of a carbocation, and the third step is carbocation capture by a nucleophile. These 3 steps tend to repeat themselves over and over and over again. So even when the substances change, we still see a lot of the same things. Alcohols get protonated, the water leaves to form a carbocation, and then the carbocation gets captured by a nucleophile. You kind of need to memorize those. And you also need to understand energetically what's going on here, that this energetic diagram is also something that you should be able to generate. And if it's an SN1 reaction, it will have this same general feature. Notice that I didn't bother to put any numbers over here on the y-axis. It's not important exactly where you draw these, but you should recognize the first step is fast and easy. The second step has this large activation barrier, so it's slow, and you have to go uphill, so that's hard. And the third step is fast and explosive. Now you go way downhill in energy. And the total energy you get out of this reaction is the difference between the starting point and the end point. And you might ask yourself, why on earth would the carbocation form when it takes it to such a high energy spot? And the answer is, well, the carbocation can, and we can pretend like it can see the future. And I'll explain more technically what that really means later on. But for now, if there is a later opportunity for the molecule to drop to an overall lower energy state, it will momentarily pass through a higher energy state on its way to reaching that lower energy state. So this process is still spontaneous because I started at a higher energy state than I ended. So it's going to happen. How fast it happens depends on only one of these 3 humps. And this is the concept that is important to chemists, both biochemists and organic chemists, the concept of rate determining steps. So the rate determining step is the step that has the highest overall activation energy. And that is step number 2. Step number 2 is your rate determining step. And while I said that these labels of step 1, 2, and 3 are just there for my convenience, that you don't necessarily need to write those down, it is a great idea for you to identify the rate determining step. So consider this example. When my family, and I have 5 kids, when my family wants to go somewhere, we have to get everybody into the vehicle. And this is a laborious process. And it always takes forever. And I put it out to my wife that she's always the last one to get in the vehicle. And so I explained to my children while we were waiting for her that she is the rate determining step. That it doesn't matter how fast everybody else gets into the vehicle, she is ultimately the one that dictates when we will actually go anywhere. And she argued that, no, we wait forever for a variety of reasons. So I started experimenting with this. One of her complaints was that the kids take too long to put their shoes on. So I went to the store and I bought my 2 sons, who were young at the time, just learning how to tie their shoes. I bought them Velcro shoes. And so that way I could show experimentally that even when they had Velcro shoes, so there was 0 time associated with them putting their shoes on, basically, we still had to wait for her. And at that point, she didn't think that was funny. She said Velcro shoes are ugly, so maybe they are. But the idea is that it doesn't matter how fast or slow any of these other steps are, the ultimate rate of the chemical reaction is dictated solely by the slowest step. So in this particular process, maybe this step right here takes a full second, which is a very long time from a chemical perspective. And this first step takes a nanosecond, and this step also takes maybe 3 nanoseconds or something like that. The difference between a nanosecond and 3 nanoseconds and 1 full second is so large that if you try to speed up the reaction by changing these nanosecond quantities right here, you're still going to have to wait for this slow step. So the rate determining step is the one that takes the longest, and it involves the highest energy the highest energy activation. So why is this the rate determining step? Well, forming a carbocation is an incredibly slow process compared to everything else going on in the chemistry. And now we're ready for the simplicity that is, once you've identified the rate determining step, then you can determine if the reaction is first order, second order, third order, whatever, because all you do is you look at how many distinct compounds are involved in that rate determining step. And so this is called an alkyl oxonium ion, the alkyl oxonium ion. The alkyl group can change depending on what it is. So this is actually a tert-butyl oxonium, if I want to be specific. The alkyl oxonium ion is the only thing that has to fall apart in the rate determining step. Because there is only one thing involved in the rate determining step, that's what makes it SN1. There's just one thing involved in the rate determining step. Later on, when we look at SN2 reactions, you'll see that in the rate determining step of an SN2 reaction, there are 2 things that have to work together in order to go through that step. That's what makes it SN2. And third order reactions are very low probability because it's difficult for 3 molecules to agree to do anything. But they exist, and they have 3 different things that all have to come together in that rate determining step and coordinate their chemistry. So the last thing that we need to look at is this concept of early and late transition states. And so forgive me another cheesy analogy, but consider 2 people on a dance floor, and this one right over here wants to ask the other one to dance. And so the idea of an early versus late transition state is kind of the decision point. So remembering back to my high school days of stake dances and the uncomfortableness of that, there was kind of this moment where you made eye contact with the other person. And at that point, you were kind of committed to asking them if they wanted to dance. That would be called an early transition state. So you had made eye contact, you might not even be next to each other, but you had already kind of reached a decision point that, okay, now I have to ask them to dance. So you can kind of consider this right here as that case. So here they're going to go in and they're going to ask him to dance. In an early transition state, that occurs as soon as these 2 make eye contact. In a late transition state, you look at the person, you still haven't decided, you walk all the way over to them, you still haven't decided, and then you ask. That's a late transition state. And the reason that chemists care about this is it allows us to kind of predict, well, what does this look like when you're at that decision point? And for something that has an early transition state, when the chloride ion is still very far away from the carbocation, you're already at the halfway point. For a late transition state, the chloride ion would essentially already be in place at the appropriate distance to make a bond before you reach the halfway point. And in order to predict if something is early or late, you just look at that individual step. If it's exothermic and goes downhill, that means it's an early transition state. So this is exothermic, meaning that this acid-base chemistry, they've already reached the halfway point and decided where they're going early on in the eye contact phase. In an endothermic process, which is what's going on in step 2, it's a late transition state, meaning that this oxygen and this carbon have not decided to sever their connection until the water is almost entirely popped off the molecule. That's a late transition state. Hammond's postulate, which is one of the definitions we'll go back and fill in, states that an endothermic reaction has a late transition state and an exothermic reaction step has an early transition state. So we can now label each of our transition states as late or early. This is an exothermic step, meaning that it starts at a higher energy, ends at a lower energy, so it has an early transition state. Step number 3 also has an early transition state. And step number 2 is the only one with a late transition state. It takes, you're almost entirely over the hill and halfway down. Well, you've come a long way. The oxygen and the carbon have separated themselves physically a long distance before that bond finally snaps. So let's go ahead and fill in the mechanisms right here. Sorry, the answers. This is show the mechanism. And so this right here is the mechanism. Let's go put the energy diagram in there. Oops. There we go. So here's my energy diagram, and then identify the rate determining step, okay, which is shown above. So I have that rate determining step identified as step 2. So my RDS is equal to step 2, and it's labeled above. And then identify each transition state or as early or late, and so that's shown above as well. So I've got all the information there kind of built into the diagrams that I drew. Let's go back up here and look at these definitions now. Polarizability refers to the ability of an electron cloud to oscillate and form dispersion forces. So something that is very polarizable means it can form stronger dispersion forces. Something that is not very polarizable means that it can form only weaker dispersion forces. Miscibility is the concept of solubility applied to liquids. So it's not really good to say that 2 liquids are soluble. We use a different word when we're talking about liquids. They're either miscible or they're immiscible. A carbocation is a carbon with a positive charge and deficient an octet. Only 6 electrons. And we're going to deal with carbocations repeatedly. They are a useful intermediate in an organic chemical reaction. It's kind of a way of spring-loading your system. You go ahead and you make something into a carbocation, and then you try to get it to do everything else. So the reaction intermediate is anything that's not a reactant or a product during the course of a reaction. So that is useful in the mechanism. This right here, so here's my reactant. This is called a reagent, which is also a reactant. So these are not intermediates, but this right here is an intermediate. And these are both intermediates, and this is my product. So reactants, intermediate, intermediates, and product over here. It's just kind of a way of keeping everything straight. If we're talking about an intermediate, that means we're not quite done yet. A carbocation will always be an intermediate because you can't produce a stable carbocation and expect it not to do anything. The rate determining step is the step in a chemical reaction with the highest activation energy barrier. And Hammond's postulate, honestly, I'm not sure why this is important, but it shows up on so many ACS exams that I would feel guilty if I didn't show that to you. It's the concept of early versus late transition states. And transition states are typically just abbreviated as TS. And so an early transition state is when you have an exothermic step, and a late transition state is when you have an endothermic step. And you might ask, well, why can't you just refer to everything as exothermic and endothermic if the idea is synonymous? And I would say, you poor fool, where have you been? If there is a possibility for us to use multiple concepts with multiple definitions, we jump on those all the time. nucleophile, Lewis bases. So the more words, the better, is basically why you ended up with Hammond's postulate. For your homework, you need to look at water being mixed with each of these compounds, and decide if they're, basically you're going to reproduce this table right here, but only this last column. So you'll be given a variety of different compounds, and you just need to identify if they're miscible or immiscible, and then if they're immiscible, identify if it's top layer or bottom layer. And those should be fairly easy chalkboard problems for you to grab some extra credit points. This show a complete mechanism for the reaction of isopropanol with hydrobromic acid. This is you applying the mechanism that we saw for one alcohol and one halogenic acid to a different alcohol and a different halogenic acid. You don't have to show the energy diagram in your answer. You don't have to label the rate determining step. You just need to show those three mechanistic steps, but with different things that are not butanol and hydrochloric acid.